Welcome everyone to this week's Deep Learning Theory seminar. Today we have the honor of having Weigutian Wu. Weigutian did his PhD and I was a postdoc with Helmut. I can never say his last name in our practice, Boletsky, at ETH. And after this, as I just found out, he'll be joining industry, but in the meantime, he's done a lot of very interesting research, and particularly this paper caught my eye on covering numbers for deep ReLU networks. So I'm pretty excited about it, and hopefully you are too. After you.
Yeah, thank you very much for the introduction and also for the invitation to the seminar. And I'm Weigutian, and today I would like to present my work during my PhD, which is covering number for deep ReLU network. It's a joint work with my PhD supervisor, Professor Helmut Buskai. And start with a little bit background why I want to study the covering number of ReLU neural network. First, because neural network is very popular in both industry and in academy. And second, nowadays we are using very large network, which was trained by a very large size of data. So the pattern is that we have more data and we use more complex model. So I was interested in understanding the relation between the complexity of the model and the size of the data. So one way to do that is to use the classical bias variance trade-off. In the classical bias variance trade-off, the generalization error can be decomposed into two parts, the bias parts and also the variance parts. And if we increase the model complexity, then the bias decrease because our model have better ability to approximate the unknown target function. But at the same time, our model might be able to fit some random noise, without any generalization ability, so that the variance will increase. And there's usually a sweet spot for the model complexity, depending on the size of training data. That's how many data you use to train. And how can we measure the complexity of a model? And in the literature, we usually use three different ways. The first one is the Hardy-Marshall complexity. And the second one is the VC dimension. And the last one is the covering number. I chose to use the covering number because my colleagues did some research on this one, so I can continue. And also because when I read some papers on the VC dimension and the covering number, I found there's some gap between these two. For example, a nearly tight VC dimension bounds for ReLU neural network has already been established in 2019 by Peter Bartlett, but there's no tight lower bound for the covering number. And on the other hand, there was results using the VC dimensions to understand the generalization ability of very deep ReLU network. There's those ReLU network with fixed widths, but with depths go to infinity. These results are almost optimal, but the generalization errors still have some logarithmic factors different from the possible optimal bounds. Unfortunately, there was no results based on the covering number. So I was interested in filling these two gaps. And today's talks, I will talk about 5 different things, even though they look a lot, but they are one story putting together. I will start with the definition for the covering number and how to understand the bias variance trade-off. And then I will talk about the covering number for ReLU neural network and why ReLU neural network can achieve covering number optimality and approximation. And putting these 3 ingredients together, I will give some analysis on the generalization ability of ReLU neural network. In the end, I will introduce what technical tools I invent in order to prove all the results in the first 4 parts. Let's start from the covering numbers. So the concept of covering number is rather simple. There is the minimum number of balls required to cover a certain set. And here I have a set surrounded by black lines, and it was covered by some red balls of different radius. And we can know the complexity of the set possibly by 2 different ways. If we use balls of the same radius, let's say 1, to cover a different set, then the more complex the set is, then the more balls we require. This is one perspective. And another perspective is that if we use a decreasing radius balls with decreasing radius to cover the same set. Here, for example, here, I use different radius to cover the same set. And the increase of the numbers of balls also tell you some information about the set. And how can we use the current number to understand the bias variance trade-off? Okay, I try to understand it from the framework of nonparametric regression. Let's say we are interested in the regression function G, which could be a mapping from, for example, the CT image to the likelihood of a person getting certain disease. And in practice, we couldn't observe the whole function of G, but instead we only have some samples of G. That is xi dot G of xi plus some Gordon random noise. And we have n sample of them. And in practice, what we usually do is that we try to train the models that minimize the empirical risk. And formally, we try to find an head, fn head from the set calligraphic fn such that empirical risk is minimized. Here we have to add more assumptions. That is, the calligraphic fn should indeed approximate the target functions G according to this assumption. That is, there exists of f in calligraphic fn such that the difference between G and f is less than epsilon. If these two assumptions are satisfied, then in our paper, and also in many papers in the literature, it was shown that the expected generalization error can be upper bounded by some constant times of epsilon square plus the logarithm of the current number over n. Here, the first red term is the expected generalization, and the second red term is the sums of the bias and variance. Let's focus on this inequality for now. So the generalization error can be upper bounded by the bias, measured by the approximation errors, plus the variance measured by the logarithm of the current number over n. So in order to understand the generalization ability of neural network, we have to get two ingredients. The first one is the current number bound for the ReLU neural network, and that's why I was interested in the current number. And the second one is the error bounds in approximating the regression functions. This belongs to the problems of network approximation, which have a lot of paper on it. So let's try to get these two ingredients in the following. So what's the current number of ReLU neural network? In order to do that, we have to define what's the class of neural network we consider. A neural network is simply a concatenation of affine mapping and nonlinearity. And a ReLU neural network is neural network with ReLU activation function. And yeah, you can see the figures of the ReLU activation functions here, which is 0 when x is less than 0 and x when x is greater than 0. And here phi is a ReLU network, which is compositions of some affine mapping and the ReLU activation function. In practice, we don't only consider one single ReLU network, but a class of network. Just imagine, when we train the network, we fix the architecture of the network, and we try to use, for example, SGD to update the weight. That is to search through all the possible network with the same architecture, but with different weights, such that the empirical risk is minimized. And in our paper, we consider the class of network, which is RDWLB, which refers to all the network with at most W nodes in each layer, and at most L layers, which with weights lying in between minus B and B. Here, even though we say that there are at most W nodes in each layer, but it doesn't harm if we add additional node to each layer such that all the layers each layer have W nodes. And it doesn't harm for us to add additional layers such that we have exactly L layer. So indeed, here the architecture is fixed, but the definition is just for some convenience in the proof. Here, the additional assumption is that all the weights have to lie in between minus B and B. So what we get In the literature, there has already been resolved on the upper bound of the current number of this type of network, which reads the logarithm of the current number is less than some constant times of W square L times logarithm of W plus 1 to the power L B to the power L over epsilon. But this result was used to also bound the generalization error, but unfortunately, there's no lower bound available. And in my paper with my supervisor, we shown that, okay, indeed, this upper bound is tight under some mu assumption, that is when W and L is greater than 60. That means the logarithm of current number should look exactly like these forms. I will give you a quick introduction on why it looks like this. Let's give you a simple example. There's the logarithm of the current numbers of a hypercube. Here, the hypercube is minus a to the power of d, which is a d-dimensional hypercube of whose edge has length 2a. The current number of this looks like d times logarithm of a over epsilon. So why is it related to neural network? Because the parameterized space of
question.
sure.
It's like a very minor question, but just to get my head in the right space. Yeah, especially since you have this dimensional constant d. So here, like, what norm do you put on the ball? On the cube, I guess. Is it the infinity norm or Euclidean norm?
I think all Euclidean norms are equivalent. Oh,
Yeah,
yeah.
but the
Okay.
dimensional constant.
Yeah. I mean, it only change up to a absolute constant, which doesn't depend on. Maybe it depends on d.
Depends on d for sure.
Okay.
No, it doesn't matter.
Yeah.
Just if you knew. Okay.
Okay. Let's say our infinity norm because
Okay. Yeah, that's
okay.
okay.
Yeah. And by the way, if you have any question, you can stop me in
Sorry.
the
I forgot to say that. What might happen. Thanks.
Okay. And the parameterized space of RDWLB is also looks like a hypercube because all the weights have to lie between minus b and b. And we have W square L's numbers of weights. But there's one more thing. There is a change of size epsilon in the parameterized space in terms of the L infinity norms will result in the epsilon times this constant change in the realization. And therefore, the logarithm of the current number of neural network will satisfy this condition. There is W square L, which is the dimension of the hypercubes, times logarithms of B over, here B is the half length of the edge, and over epsilon over this term, because we have a difference in the parameterized space and the realization space. And that's how we get the forms of the current number. And we know that here we only get the upper bound, but for the lower bound, we will need other tools that are introduced later. So now we have the first ingredient, which is the current number of the neural network. And we still need another ingredient for the approximation. We know that the regression function G is unknown, so we couldn't characterize the approximation error. But if we know that, for example, the regression function G has some property, here we assume G to be one Lipschitz. And then we can characterize the worst case approximation error when we approximate a one Lipschitz function by ReLU neural network. And we characterize the approximation errors in our first paper in 2024, which shown that every one Lipschitz function in H101 can be approximated by a ReLU network in R1WL1 with error less than W square L square, logarithm of W altogether to the power of -1. Okay. So here the class of neural network R1WL1s are network with width W, with depth L, and with all the weights lying between -1 and 1. The line between. Okay, sure, go ahead.
Sorry, I always have questions. Yeah, I guess one question I have is, yeah, especially how does this look like in high dimensions, I guess? Like, I mean, how should I think about your result in high dimensions? Because unless
Uh,
I'm wrong, it's like unit interval.
um, yeah, I think that's a good question. I think for actually the result also holds for d-dimensional Lipschitz functions.
Okay.
I think I try to wrote some notes on it, but for example, d-dimensional holder continuous function, I believe it holds, but I didn't try to write it because you have to do some multiplication, which is very complicated.
Okay. Okay. Cool. Thanks.
Yeah, you're welcome. Um, and yeah, this is our error upper bound. Before we proceed to put these two ingredients together, let's ask whether these two ingredients are the best we can get. The current number bound is tight, so we couldn't do it better. But how about the approximation error bounds? Indeed, we can also use the complexity argument or reasoning to show that this upper bound is optimal. The intuition is very simple. That is, if every element in the set A can be approximated by an element in the set B, then the complexity of B should be at least comparable to that of A. Um, it makes sense since you couldn't put 1 liter of water into, say, 500 milliliters volumes of a bottle. So if we put in the context of our research, then it looks like this. If every one Lipschitz functions can be approximated by a network in R1 WL1 with approximation error epsilon, then the covering number of the ReLU network for this epsilon as a covering ball radius should be at least comparable to the covering numbers of H101. Also for this epsilon as the covering ball radius. So we have an inequality here, and we can plug in the covering number for the neural network and also a covering number for one Lipschitz function, and which is provided in the literature too. Then we shown that actually our approximation result is optimal and couldn't be improved anymore. So now we know all our two ingredients are optimal and couldn't be improved, so we can put them together to get the generalization error bounds for use in regression. Okay, let's consider the regression estimation of one Lipschitz functions for and noisy
Can I just
observation.
ask one question, just my personal intuition? I said this was like the 100th question. Well, why do you want the functions to be in the subleft space? Like, why do you need this?
Actually, it's not. Yeah, it's a good question because here we indeed consider the one Lipschitz function. It has nothing to do with subleft space, but because this symbol is shorter in comparison to LIP, so we chose it to use this symbol. Yeah,
Okay.
yeah,
Okay.
but there's a good question.
Cool. Thanks.
Yeah. And what we need to do is to plug in our bounds for covering numbers and our bounds for the approximation error. But at the same time, we have to choose how the network looks like for given n. Here, the network we chose are R, 1, D, L of n, 1. Here, D is the absolute constant we chose beforehand. And this means that the width of the network wouldn't increase with the number of samples. And L of n is the depth of network, which increase with respect to the number of sample. And L of n is chosen such that the bias terms and the variance terms are balanced. That is, they should have the similar order. If we chose our network in this way, then we can show that the expected generalization errors is at most some constant times of n to the power of -2 over 3. And indeed, the race is optimal because the estimation of one-Lipschitz functions has already been studied in the literature, and they have shown that the race is exactly n to the power of -2 over 3. In our paper, we also discuss why we get such optimal regressions. That's because we have the optimal approximations, and we try to give a relation between these two. And our result is built on the classical Young-Barron theorem. So how does
Wait,
the,
can I ask one
sorry.
more question?
Yeah.
Just to check, so to understand the rate, but here you're measuring the error in the squared L2 norm, right? So would the rate technically be one half, like a factor of, should be like n to the one third? Like, I mean, if you take like the L2 norm instead of the squared L2.
No, I think it's the square. Let me see how the form looks like at the beginning.
Yeah, because
Yeah,
the
because I didn't take the square roots. I mean, if you take the
exactly.
square roots, then there should be n to the power of minus 1/3. But
Yeah,
here I
that's not, yeah.
don't use the square roots.
Okay, just checking. Otherwise, that rate is like crazy fast.
Okay.
Okay, cool. Thanks.
And yeah, here's the compare. Okay, please go ahead.
Hi, so I just want to know, how do you show that the rate cannot be improved? Do you mean that the exponent minus 2 over 3 cannot be improved, or just like what if there's, say, another factor of log n or something like that? So
Okay.
so are you only showing that the exponent cannot be improved?
So what do you mean additional factor log n? Because here the c is a constant, doesn't depend on n. So the raise in terms of n is exactly n to the powers of minus 2/3.
Yeah, but by at most, you mean, there could be some other growth rates, like this n to the minus 2 over 3 multiplies or divides, let's say log n or something like that, which
So it
which
couldn't be
this
divided by the log n because it has been shown in the literature that it should exactly be n to the power of minus 2/3 times some constant not depending on n.
so it's like there cannot be any other factors,
Yeah,
you're saying.
yeah. I mean, there can be other factor, but the additional factor cannot make the generalization error smaller, but it can make it bigger. I'll show you later in the literatures. Another result is to show that the generalization error is at most some log n to the power of 6 times n to the power of minus 2/3, which is weaker than the result we get.
Okay, I see.
Okay. And in
I
order
see.
to
Thank you.
You're welcome. And in order to get the optimal lower bound, you can refer to Young-Barron's result, which give you a generalized frameworks to understand the best possible sample complexity rate in the estimation of a very large set of class of functions. And let's compare our result to what we get, also to what is has been going in the literature. In the literatures, in particular from Kollers and Langer in 2021, they fit network in R1D-Ln. Here the D and L of n could be different, but the network they use don't impose any constraints on the weights. There is the infinite here in red. And their analysis is based on the VC dimension because the class of network they use as infinite Curry number. And they shown that the generalization error bound is upper bounded by at most some logarithm factors times n to the power of minus 2/3. This was the VC dimension bounds on the generalization error I mentioned at the beginning. So now we have characterized the current number of neural network and to show that neural network can achieve some optimal approximations. And we put these two results together to characterize the generalization ability of real neural network. And in the remaining times, I would like to introduce the tool I use to prove all these results. And I use mainly 3D technical tool. The first one is called the depth weight magnitude trade-off. And the second one is the natural realization of one-dimensional piecewise linear function. And the last one is called the big extraction technique. Let's start from the first one. Now, in the previous parts of the talk, you may be curious why the network I use has weights lying between -1 and 1. Because sometimes it will be very difficult for you to construct a network that achieving certain things under such a constraint. And I get rid of this problem using the depth weight magnitude trade-off, which shown that ReLU network with large weight magnitude can also be realized by corresponding deeper network of smaller weight magnitude. And here you can see in the red part, on the left-hand side is a shallow network but with a greater weight magnitude. And on the right-hand side, which is a deeper network of depth L plus L primes, but with a smaller weight magnitude. Here, the B primes is chosen to be 1 in our case. So this is the first ingredient, the first tool. And the second tool is the realization of
Sorry, can I just ask one more question? So I was trying to read that very quickly. So what's the relationship between B and B prime?
A B and B prime can be anything. I mean, there don't have to be a relation.
Mhm.
That means B prime can also be much greater than B. In that case, we'll rather use the first inclusion.
Okay.
If B prime is much smaller than B, then we may use the second inclusion.
I see. Also, there's a question in the comments, I think, but some similar flavor.
Okay. No, okay, actually, okay. How large must L prime? I mean, L prime can be anything, and it only have to be a non-negative number.
Mhm. Thanks.
You're welcome. So this is the first tool. And the second tool, I mean, you may find very familiar because I suppose you also use it in your paper. I read your paper. So it's the realization of piecewise linear function. So what is the piecewise linear function we consider here? And here, the function in red is piecewise affines on each interval, say from -infinity to x0, from x0 to x1, blah, 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 from x5 to x infinity. And x0 until x5 are called the breakpoints of the piecewise linear functions because the slope of the function can only change there. Here we have to impose one more constraint, that is the function have to be constant in the interval from -infinity to x0 and from x5 to x infinity. I mean, just for technical reason, for convenience. And this is how we define the set of piecewise linear function. We write it as sigmas of x dot E. Here, x is the set of breakpoints, and E is the L infinity norms of the piecewise linear function. So the function I just shown you belongs to the set sigma of x0 blah 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 x5 dot E. And in our paper, we shown that this type of function can indeed be realized by the ReLU neural network. That is, sigma of x dot E can be realized by network in R 1.20U 30V 2W, given that condition 1 and 2 can be satisfied. I'll explain what condition 1 and 2 mean. Condition 1 means that the number of ways should be at least the number of breakpoints, because you can see that is the parameter for the width and v is the parameter for the depth, and u square v will be roughly the number of ways of the network. I mean, this condition was also requires in Lipschitz's paper in 2022 and also in your papers in 2024. But I suppose both of your papers don't care about the weight magnitude, so you don't really control how the weight looks like. And so in our paper, we try to characterize exactly how W has to be in order to realize a piecewise linear function with our infinity norms and most E. So that's how we get, and that's why we impose another condition 2. And this is the second technical tool we developed. indeed, by combining the weight magnitude trade-off and also this piecewise linear function realization, we can get a lower bound on the current number of ReLU network. But in order to achieve the optimal approximation, we still need another tools that is called the big extraction technique. The big extraction technique was first introduced by Peter Bartlett to lower bound stability dimensions. And it was also used to make some constructed approximation in the literature, using the neural network to approximate certain function. And the technique consists mostly of two components, and that is the encoding and the decoding. For the encoding part, let's say you want to encode a binary strings 10100 as a single number. How should we do that? Intuitively, we just write it down as a binary number. And what they did is that they write it as 0.10100 of its binary form. That's the first component. And the encodings will then be stored as a weight of the network. The second component is the decoding part, where they have to implement a ReLU network to decode the encoding. And in their paper in 1998, they construct a network D, which take input of the encoding and also another input L, so that the output will be theta L, where theta is the string they encode into the encoding, and L is the inputs of another input of the decoding network. But there was a problem in applying the bit extraction technique in the literature for our constructions, because the weight magnitude of their decoding network have to grow exponentially in the network depth. And it will result in the network with really great weight magnitude, which means a really great current number. And we solve it by a new construction such that the weight magnitude no longer depends on the network depth. So we can achieve the same functionality, but with a smaller network in terms of the current number. So how did we manage to do that? And the idea is quite simple. We use a base 3 encoding instead of base 2 encodings. And that is, when we encode the same string, 10100, we encode it as a trinary number, 0.10100. And let me show you why it gives you some advantage, even though it looks quite simple. Okay, let's say you want to encode two strings, S1 to be 10000 and S2 to be 01111, and see how the encoding difference using base 2 and base 3 encoding. If you use the base 2 encoding, then the first encoding B1 will be 2 to the power of -1. And B2, which is the encoding of the second strings, will be 2 to the power of -1 minus 2 to the power of -n. The difference between these two encodings is 2 to the powers of -n. Yeah, I mean, even though they are very different because the first digit of them is already different, but the encoding of them are very close to each other. In other words, sorry.
Okay, so I ask one question.
Yeah,
but maybe after you make your point, sorry, I interrupted back then. But why not consider like a base P for some prime, large prime P? Would that improve it then?
No,
I don't know. It just came to my head and I had to ask, Because then
I think the problem here is that the difference between those two encoding are too close, and you have already been solved by using base 2 encodings. Yeah, I mean, you can definitely use a larger base encodings, but probably in that case, for example, if you use base P encoding, you might want to encode a P-1 array strings rather than just a binary string.
Yeah. Okay, yeah, fair enough.
It might be helpful, but that will take a lot of time, and I'm not sure that you increase the rate.
Okay, yeah, fair enough. Thanks.
Yeah. So here, if we are only curious in the first digit, then the decoding network have has already to have a Lipschitz constant of at least 2 to the power of n, which is not ideal. But what happens if we use base 3 encoding? Here, B1, which is the encoding of S1, would be 3 to the power of minus 1, and B2, which is the encoding of S2, is less than 2 times 3 to the power of minus 2. The difference between these two encodings is greater than 1 over 9, which doesn't depend on n. So that means maybe our maybe the Lipschitz constant of our decoding network can be at most 9. Indeed, we can construct a decoding network with Lipschitz constant 9. So this is how and why we make the improvement on the big extraction technique in the literature. And putting these 3 technical tools together, then we can achieve the optimal approximation error. And yeah, I think that's all for my talk. Yeah, I went a bit faster than I expected.
That's good. Good.
I welcome questions.
Thanks a lot. It was a really interesting talk. Let me this applause reaction. Yeah, I have some questions. I have one question, or maybe two, but let me just ask if anyone in the audience has a question.
So I have a quick question.
Okay.
Can you go back to page 31?
For sure.
Yeah, so I see you mentioned my paper with Dr. Krasios here. So I was just wondering, have you tried bounding the weights using our approach? Because in our paper, we also give an approach for constructing these piecewise linear networks using U and V neurons in 2 layers and then approximating around U times V segments. Have you tried bounding and using that?
Actually, I believe the technique you use and the technique from Lipschitz might also result in the upper bounds of the wave magnitude. But the bound is, the difficulty is not in the idea, but rather in the calculation. It took a lot of time to make all the bounds clear and correct. Yeah, so I do believe that your technique should work. But I just don't have the energy and time to make sure that it works.
I see. Because one reason we didn't give this bound was because it wasn't obvious that this was easy to compute in any way. So
yeah, indeed.
just
Yeah, and indeed, using this bound alone wouldn't get the lower bounds of the current numbers. I still need to apply the wave magnitude depth trade-off. Yeah. Yeah.
Can I also ask a question? It's also related to the paper you mentioned. Actually, yeah. So suppose instead of you bounding like the network weights, the parameters, I guess, and you bound, say, the Lipschitz constant, so of course bounding the weights will imply bounding the Lipschitz constant, but like that bound is, could be, there's a big gap between those two objects. Yeah, I was curious, like, do you have any idea of how you get lower bounds for the covering number of, say, L Lipschitz networks with, I'll say like lambda Lipschitz networks with L layers and with W, instead of like, so if you wanted to like constrain the capacity instead through the Lipschitzness instead of like through the realization instead of through the parameter space, because right now you constrain through the parameter space. Like, do you have an idea of how to do this? Because actually I'd be curious, but I don't know how to get the lower bound.
Yeah, indeed, I have no ideas, but I did read your papers. I think the way you use the Lipschitz continuous network to approximate some target function is to show that is to consider a subset of the realization. I think a subset is like some piecewise linear functions, which can be realized exactly by Lipschitz continuous network.
Something like that. Yeah.
Yeah.
Something like this.
Yeah, I mean, you can definitely make a lower bounds of the current number of this subset, but to make a lower bounds on all the Lipschitz continuous ReLU network, I think it will be super difficult because you have no idea. We have no idea how large the set looks like.
That's fair. Yeah, because I know there are some lower bounds for these like D2 Kolmogorov in like the 40s or something. or the general Lipschitz functions on a metric space. Um, but yeah, I don't remember. Anyways, okay, no, I'm just curious if you had an idea. Cool. But otherwise, I think those are all my questions. And I have to say the talk was quite nice.